on. Okay, so let me make sure I got the right one. All right, yeah, so this is dealing with beam behavior. Let's go into this section. So what we talked about last time was beam behavior, bending, shear, and deflection was the aspect that we didn't get a chance to get into. So I want to pick up with that, although I'm just going to really quickly review because we didn't get a chance to do any bending and shear problems. So if you want to look at a few today, just let me know, okay? So we talked about the behavior of bending, and we looked at bending stress, and we looked at shear stress. So deflection using standard formulas we have not used, so I want to take a look at that. So let me kind of buzz through this a minute. Couple of key ideas there is the equation. I want to show you. This equation here is going to be key when you're dealing with bending stress, okay? So if you haven't had a chance to look at that, that's going to be your key equation for bending stress on a beam. So it's just your moment, your applied moment times your C value divided by I. Who can tell me what C is? Anybody remember what C is? Nobody remembers? Okay, let's go look at that real quick. So if we looked at that from a diagram standpoint, your cross section, let's say you have a rectangular type of cross section. What is that line called that I just drew? Anybody tell me? For the rectangular cross section?
0.
Well, it represents 0 something, that's correct, but there's a name for this line.
Let's start with a V.
No, it's called the neutral axis.
Okay.
And it's neutral, Jacob, because as you said, that means that there is zero shear going on at that point, okay? Or zero, okay. Let me take that back. There's 0 moment going on. There's actually maximum shear going on there, okay? So for a rectangular cross section, where would your neutral axis be?
Vertical?
Well, it would be right in the middle from the top to the bottom, okay? Another way of looking at your neutral axis is that's the same thing as the centroidal axis for a rectangular shape. Now, when you get into complex shapes, that centroidal axis may shift a little bit up or down, okay? So that would be your neutral axis. So C, in that equation we were just looking at, is defined as the distance from the neutral axis, right? From the neutral axis out to the edge fiber of your beam. So you could look at a C value anywhere from here, which would be 0, out, so up to the half of the depth, okay? So as you go from the neutral axis out, C is going to increase. So when you look at this equation, M is equal to C over I. If C is increasing, then the stress bending is also increasing, okay? From a design standpoint, you're normally looking at what's happening out here anyway, okay? So we're usually looking at what we would be calling the maximum bending stress. Does that make sense? Everybody?
Yeah.
Okay.
So
All right,
basically this is like strengthening, finding the areas you need to reinforce the beam.
Well, not necessarily that. What it's really telling you is if you have, let's look at this on a cross section. Or actually not a cross, we're looking at a cross section. What we're looking at there is, remember, if you have a force coming down on this guy, right? It's producing a bending moment, okay? And what happens is, so that that beam doesn't rip apart or it doesn't deflect too much, the material has to develop stresses in here to counteract that bending moment. So this is a counteracting thing that will counteract the applied moment, okay? So you're going to see like allowable bending stresses, so that if you're designing a beam and you've got a moment of so much applied moment on there, and you calculate this number and it exceeds your allowable, that means you would have to change what's going on there. So if I've got a situation where my my bending moment is being exceeded or by the allowable, then I've got a couple of ways I could fix that. So how could you fix that if you've got a situation where, you know, this is not in compliance? How could we fix that? Look at this equation. If for instance, if you can't change this, if this is fixed, okay, if you can't change that, how could we get this number down?
Thicken the beam.
Yeah, in other words, what you're doing is changing this. If I can increase the moment of inertia, it will decrease this. So if you increase the moment of inertia, you would be decreasing your bending stress. So that's one way of doing it. Now the other way of doing it would be to somehow decrease the moment, but that would mean you'd have to change what's going on in terms of your loading scheme, okay? So
Yeah.
those are some things to think about. That's what a designer would have to look at. Notice also, this equation doesn't even bring in the material itself, right? You notice that? Because you're not looking at a modulus of elasticity. So if we had a modulus of elasticity in here, we would have a situation where we would be looking at that, okay? Does that make sense?
Yeah.
Okay. All right, so that's an important process, or that's an important principle right there. But this equation is really straightforward. Just remember that C is the distance from the neutral axis out to wherever you're looking at your stress. But a designer usually wants the maximum stress. So they want to look at the edge fiber of the beams. Also, when we look at this, because this beam is being kind of rotated, it's kind of doing this. What's happened at the top of that beam versus the bottom of that beam? What's happening at the top? This is pushing this way, and this is pulling this way on the beam. So what's going on there?
Compression.
Yep, you got compression at the top, and we got tension at the bottom fibers, okay? If this is the same distance from here to here and here to here, then the compression and the tension are equal. They're just going to be opposite sign. But if your neutral axis moves up, you may have less compression than you have tension, okay? So that might come back to materials, because you may have a material that holds up better in tension than it does compression, all right? Does that make sense, guys?
Yeah.
Okay, so let's move back here. Let's go back to here. So this equation, simply, that's your bending equation, okay? So that's your bending stress. Remember the stress units, PSI, KSI, pascals, kilopascals. That's your applied moment. That's your distance from the neutral axis, okay? All right, so we went through some examples. I could do some other examples today. We can look at that if you want to, but we will definitely, that's what we're going to concentrate a lot on Thursday, okay? So make sure that you do those problems, the stress-related ones, the bending stress-related ones out of this chapter, okay, for this Thursday. So the other thing that we talked about was shear stresses that develop in a beam, because remember that beam is also trying to be ripped apart, and so in order to resist that ripping, you're going to have shear stresses that develop. Now that equation is a little bit tougher to deal with. It's this one right here, where your shear stress Sigma V is your applied shear times your static moment of area divided by I times B. All right, so let's look at that one. That one's a little bit harder, and I'm gonna go through some things on that with you as well. So again, that's your shear stress unit, which would be PSI, KSI, or Pascal, kilopascal. V is your applied shear force on your cross section, so that's whatever is being considered. Q is what we call the static moment of an area with respect to the centroidal axis, and that's the tough guy, and we'll take a look at that too. I might want to do another problem or two with you guys on that one. And I is your course your moments cross section moment of inertia, and B is the width of the beam at the location of where the neutral axis is. So that's your width at the neutral axis. So it's not dependent on the part itself, it's just where the neutral axis is crossing the part. Okay, so Q, remember, is equal to the area of consideration times the centroidal distance. And if you have complex areas, then you can calculate Q's of each complex area and you can add them to get your total Q. So let's take a look at Q again. And then I'm going to show you something that's also pretty interesting about the static moment of, or the, about the shear stress. Okay, so let's go back to this guy. All right, let me clean this up a minute. Okay, so what we're looking at there again is if we have a very simple rectangular cross section. Okay, so remember the equation that we're looking at for shear, it's your shear applied force times your static moment of area divided by I times B. So in this beam, let's say that's my neutral axis right there. Okay. And this is neutral axis. And this is your height of your beam, and this is your base of your beam. Okay. So Q, usually you're going to be looking at the total area here. So if I'm looking at this area right here, Q is basically going to be this area here, okay, that cross-hatched area. So the area of that is going to be base times h over 2. Does everybody see that? So it would be this base times h over 2, because this h is the total, okay? So also then Q, if you look at Q, that equation, it says Q is equal to area times your centroidal distance. So in this case, the centroidal distance would be that distance, which would actually be h over 4. So what we would have in this case is we would have B times h as your area times, in our case, h over 4. Okay. So this would be for the total cross section here that we're looking at. Okay. Does that make sense for everybody? This guy's the hardest guy to deal with. Can anybody tell me what the unit of this would be? What's the unit of area? Something squared, right? So if this was inches squared and this was inches, this would be inches to the third. Does everybody see that?
Yeah.
So Q is always going to be inches to the third. This will be inches to the fourth times inches. That's going to be inches to the fifth. inches to the third divided by inches to the fifth is going to yield you pounds per square inch. Okay, so this does agree with the PSI. Okay. So let me show you something else may happen on this one here. Let's put some numbers to this. If they ask you, and there are a couple of times that Tom will ask you this, let me back this up a minute. I don't know, it's probably not going to work. Let me erase this here. I'm going to put some numbers to this so that we can kind of calculate a real area here, so we can see how this works a little better. So let's say in the problem, they give you, let's do that. Let me give you, hold on a sec. Yeah. If they give you some numbers here, right? So let's say this is 10 inches and this total is 16 inches. Okay. So if that's the case, we're going to calculate a Q real quick. I want to spend a little bit of time with Q because that is really the hardest thing to deal with in this equation. The rest of it's pretty simple. So that means that if this is truly centered, this is going to be 8 inches here and 8 inches here. Okay. So let me I'll just erase this guy. All right. So if we're looking at the total Q here, what we would have for that case, we would have 10 times 8. That would be my area, correct? What would be the distance from the neutral axis to the centroid of that area? The centroid of that area is going to be right in the middle. So what would that distance be there?
4.
It would be 4. Okay, so in this case, for this beam that we're looking at an area of 10 times 8 times 4. So we would have 320 inches to the third. Okay, that's not too bad, right? So let's change this a little bit. What they'll very often do, you'll see these problems, and I just want to go through this so you understand what's happening with this. Very often you're told, okay, I don't want to look at the total shear. I want to look at the shear going on up here. Whoops, that didn't draw for me. Let's try that again. I want to look at the shear right here. So what they're telling you is, I want this area right here. So they'll give you a distance. They'll say like, I want to go 3 inches up. Okay. So what you're doing is you're taking 3 inches minus the 8. So that's giving you, what, 5 here, right? So my area is now 10 times 5. Everybody see what I'm doing? So we're just considering the shear in this region. So what would be the distance from there to there? What would be the distance from here to the centroid of that area? Well, half of this would be 2.5, right? Right? 2.5 from here to here plus 3 would give us what?
8.
No.
2.5 plus 2.5 plus 3.
No. 3 plus 2.5.
Oh, it would just be 5.5.
Right. So then your distance would be 5.5. So what you'll notice, if you remember, we calculated 320, I believe this is going to drop. So this comes out to be 260 inches to the third. Okay. My point being is you don't normally do this kind of stuff, okay, with cues, but there are going to be some problems in the book where he's asking you to do that, okay? So you need to understand how to handle Q in that case. Most of the time you're going to be looking at Q in the total value there, okay? Is everybody okay with that?
Yeah.
All right. So here's another case that you can look at with Qs, and I want to or not with Qs, but actually with shear. There's another equation for shear, which I don't have on your notes, but I just want to show you. This is a very good one to use, and it has to do with rectangular cross sections. If you have your book, let me look at, try to find this page for you. Okay, at the back of your chapter on page 413, they show you an equation for shear stress that is different than the shear stress that we're looking at. So I'm going to go through that derivation for you. And this only applies to rectangular cross sections. But it is very convenient when you have a rectangular cross section because it's a lot simpler than using the other equation. So let me clean this up a minute. Actually, I'm just going to take everything out, redraw it. Okay, so for a rectangular cross section, let me just take that out too. All right, so if you have a truly just rectangular cross section, all right, you can use a very simplified shear equation. Okay, so there's my rectangular cross section. That's not a very good location. Drop that down a little bit. Okay, that's a little bit better representation. So that's my neutral axis. Okay, so there's my neutral axis. And if this distance is B and the total distance is H, okay, so H is the distance from here to here. So there's two equations you can use here. You can use, oops, let me undo that. We know that shear stress on a beam is going to be equal to V times Q divided by the moment of inertia times B. But if you look on page 413, they show you another equation that says shear is equal to 3V over 2A. Okay, so these equations are exactly equal as long as you have a rectangular cross section. Okay, if you don't have a rectangular cross section, then they're not equal. So you have to understand that first. Okay. So, but let's take a look at how this got converted into that. Okay. So if we look at the definition of Q, we just looked at that. So we should be able to write the definition of Q. So Q is the area of this, and we're looking at this total cross section right here. So we're looking at this section right here. So the area would be the base times half of the height. Everybody agree with that? So the area of that crosshatch is base times half the height, right? And the distance from the neutral axis to the centroid would be half of height divided by 2. So that would be the same thing as h over 4. So if we simplified this, what we would have is base times height squared divided by 8. Okay? So I got my area times my centroidal distance from neutral axis to the centroid, and I just multiply those, I get base times height squared divided by 8. Everybody follow me so far? So what is the definition of I for a rectangle? It's 1/12 the base times the height cubed. 1/12 the base times the height cubed. So if we plug these two values back into this equation, what we wind up with is this. We have V times base times height squared. I'll bring the 8 down here. And then the moment of inertia is base times height cubed. And the 12 will come up here. And then we have base. So what we get is V. And then we get base times height squared times 12. Base times base, that gives us 8. Base squared, height cubed. B, or I'm sorry, I've already did the B, okay? So some of this will clean up. That cancels, you're left with just H. That cancels, you're left with B. And you can simplify that. 4 goes into 8 2 times. 4 goes into 12 3 times. So you're left with 3V times 2, and base times height is the same thing as area. So for a rectangle, instead of using this, you can simply use this equation, but you can't use that under any other situation. Okay, does everybody understand that one? This is a really cool equation to use. And there's going to be quite a few instances in this book on some of the problems that you'll get into where you can use that one directly. Okay. Everybody okay with that?
Yeah.
Okay. All right, let's look at one other thing. I also want you to note on equation or on page 413, this is also something we didn't talk about last week. For bending, they show you a different equation. So let me clean this up. I'm going to give me a new page here. So for the bending equation, we know that bending stress is your moment, applied moment, times C times I. But you'll also notice on the top of page 413, they have another equation here that says M divided by S. S is defined as what they call a section modulus. A section modulus. And what's cool about the section modulus as defined as I divided by C. So what you have in a lot of equations is they'll give you in tables, you can look up the section modulus, and you notice that if you displace that for that, you get the section modulus. You can just look this up. So you don't have to look that up and that up. Okay, I'm going to run through an example of that where we use the section modulus. Okay, so does everybody see if you took the section modulus and you put I over C, I just stays in the bottom and C flips. So these are exactly the same. Okay, and that has nothing to do with the shape of the cross section. Okay, it strictly has to do with the I value and the C distance. So this is more convenient. If you can look this up, this is way more convenient. We'll go through an example here problem, okay? In fact, why don't we do that right now? Let me grab a problem and we'll check that out. Let's see. Let me find one that we can look at. We can do that. Let's see. I want to look look at problem, let's see, give me a sec here. Had everything organized last night, and I I'll be right with you. Trying to find one that really works really nicely for this. All right, we're going to look at a problem. I think this is problem 37 out of your book. So this is, let me grab the page for you. Yeah, actually, that's not one I want to look at. I'll tell you what, maybe I'll wait on this and we'll do one another time. Maybe I'll do this on the board with you. Okay. So, but we'll figure that we'll work on something else. All right. So there's some problems in there though, but you can actually utilize this though. Okay. So we'll take a look at this on Thursday. Sorry about that. All right. So let's go back. The next thing I want to handle is deflection. So this is the stuff that we didn't get into the other day, was deflection on a beam. So we want to look at that, and then we're going to jump into a little bit on chapter 13. Okay. All right. So let me let's see. Where were we? So I added this beam deflection stuff to your notes. So if you have the old chapter 12 stuff, I put this up there last night. Okay. So you have this in your notes. It goes up to here, but it doesn't go further. So I added this. So if you want to pull that up, you can have that now. So another thing that they talk about in chapter 12 is beam deflection. So it's going to be a very important thing as far as the functionality. And we talked a little bit about that last week, that, you know, if you're on certain structures, you can actually feel deflections from a beam. And so that can be something that's really, you got to think about. The one thing that's important about beam deflection is the appearance. I mean, people see beams bending, such as in a highway bridge or something, and they immediately might think that that's kind of a failure kind of thing. So if it's too much deflection, or it looks like it's too much deflection, it might be a bad thing. Maintainability, durability, comfort, all of these things are dealing with beam deflection. And like I said, if you're on a beam that's deflecting from a comfort standpoint, you may not think that that's that it's right, that it may be going into a failure. So an excessive beam deflection can definitely cause a beam to behave in an unsatisfactory way. So things like cracking can occur, particularly in like ceilings and walls. So if you have a roof truss or beam that's supporting things, it could develop cracking in your drywall, those kind of things. And of course, we have perceptible vibration or that movement. And I can sure you guys have all been on bridges, I'm sure, that you can feel them move. And that's not real comforting sometimes. So one of the things that a structural designer needs to do is they need to be able to calculate that deflection in order to be in compliance with any kind of building code that you would have. So there are going to be what we call allowable amounts of deflection, and then we need to be within that. So in your building codes, they'll spec out like how much deflection you can have allowable based on whatever your span is. So your total distance of that beam. So there's a couple of different methods that are used to calculate beam deflection. We're not going to get into it very involved. I'm just going to show you a real simple one. But they have what's called the moment area method, which is a much more involved methodology, and it allows you to calculate deflection at any point along your beam. Now, most of the time you're looking at maximum deflection, but this method will allow you to get any type of deflection along it. The other one is to use what's called a standard formula method. And the standard formula method is nice because it's just methods that have been developed that allow you to just plug stuff in, or formulas that you can look up. And that's the one we're going to look at. So on your in your book, we're going to look at page 406, and that's where we're going to find our standard formulas. So these formulas have been written to calculate maximum deflection of a beam or deflection associated at a specific point. So that's important to understand because it may not be talking about maximum deflection. It may be talking about just at a specific point. So there's a lot of different sources. You could probably go to the internet and find them. The American Institute for Steel Construction, the AISC manual, has a lot of different formulas, just tables of these things. In your book, on table 12.1, which is on page 406, you'll see just a few of these. And again, we're not going to look at this in very much of depth. But so one thing to note when you look at those formulas, hopefully everybody's got table 12.1 popped up because I don't have that on my sheets. But those formulas, the magnitude of that deflection is going to be inversely proportional to what we refer to as the beam stiffness. And beam stiffness is defined as E times I, modulus of elasticity times the moment of inertia. So in other words, as that number increases, your deflection will go down. So if you look at that, those tables there are the equations for the different case loadings. On table 12.1, you'll notice that EI is in the bottom of the equation. So essentially what we're saying is if we look at a picture here, let me clean this up. So first off, if you look at a beam, remember, if you're looking at a simply supported beam, if this is your normal beam without any loading on it, when you load that beam, what we're saying is, due to the loading, you're going to get some kind of deflection going on here. And maximum deflection doesn't always occur at that point, but this is what we would call beam deflection, okay? So you could look theoretically at the deflection here or the deflection here, even just depends on what you're looking at. But just understand, because of the loading scheme, you're not always going to have maximum deflection at the mid-span, okay? Now, if we look at those equations, by the way, they use in that equation, they use big delta. That's the same thing as what we typically call little delta. So that's your amount of deflection. So that's your beam deflection. and that's going to be rated in a distance, okay? So that's typically going to be in inches because you're not talking about huge amounts of distance. If you are, you've got problems or you may have failure. So if we look at any of those problems, you'll notice, or those case loadings, you'll notice there's a bunch of variables up here, but everything is divided by EI. That's your beam stiffness. So whatever is up here, and I'm just going to call that K for that's just variables. What we're saying is as this increases, this decreases. That's what we're talking about by being inversely proportional. So if you do have more deflection here than you want, most of the time what you can do is increase this. So by increasing this, I could go to a different material, say from wood to steel, that would increase this. Or I could increase the depth, which would increase the moment of inertia, and that would decrease, okay? So that's what we're talking about. So as we go back and look at these, all right, beam stiffness is really, really important. And the larger we can get that EI value, that beam stiffness, the smaller we can get the magnitude of deflection. Okay? But like we talked about other things, as you do that, there's trade-offs. If you're going to a bigger depth, you have to have more distance to manage that beam. If you're going from wood to steel, there's going to be cost issues. So there's a lot of things that can happen. Okay. So magnitude of your deflection is going to be really typically small. Okay. And again, it's usually rated in inches. When we use those problems out of that table 12.1, you have to really make sure that you are dimensionally correct and everything agrees. So usually you want to work around the modulus of elasticity because that's going to be the one that kind of defines what units you want to be in. So loads, typically you want your loads in pounds, okay, or kips, could be kilonewtons. If you've got uniform loads, you're going to probably want to put those in pounds per inch or kips per inch. And your spans are going to be probably given to you in feet, but you're going to want to convert those to inches. And by doing that, everything that you get into those equations will be correct. And then usually your deflection will be in inches. Okay, so that would be kind of the main things we're looking at there. So your actual beam deflection then is going to have to be compared to what we call allowable limits. And as we said, building codes and other specifications are going to typically give you limits on what deflection you can have, and it's usually based on several things, either live loads or dead loads or type of material used. So if we go to page, let's see, if you go to page 12.2, you can see that there is a table there that defines deflection limits or allowable deflections based on conditions. So you can see for live loads, you have values. If it's a roof member or if it's a floor member, you have snow load values, and you have dead plus live loads. Kind of a general equation that's nice to remember is in general that deflection is based on the allowable deflection would be 1/360th of the span. But that's, again, that's not always true. You can see that depends whether that's like, for instance, plastered ceiling or non-plastered or those kind of things. Okay. So I'm going to work through an example with you and show you kind of how this works. And by the way, they also can talk about a process called superposition, where that if you have, I don't think I brought that up on here. Yeah. But if you have more than one case loading, you can actually solve it two different ways and then add those deflections. So we're going to take a look at an example here. Let me flip over. I'm going to show you how to do a beam deflection case. Okay. This is pretty simple. The biggest deal is that when you do these problems, you have to remember what units you're dealing with. Okay. But the other thing is too, you have to have the formula that'll match the case that you're dealing with. So I'm looking at a problem here. Let me draw it up. We're going to calculate a deflection based on those simple standard formulas. So we've got a beam here, and it's got a uniform loading rate on it. There's a uniform load happening right there. And this thing has a uniform load rate. So we got, dang it, sorry about that. Not cooperating with me today. So we got a uniform load, so we got loads coming across this thing, like you would have on a floor. So this could represent like a floor joist. And that load rate is 3 kips per foot. Okay. And this span is 20 feet from side to side. And this happens to be a W 12 by 50 steel beam. So if it's steel, we're going to need the modulus of elasticity. So modulus of elasticity, we're going to say for steel is 29,000 KSI. Okay. We also need the I value for a section 12 by 50. If we go back to Appendix A, in Appendix A, let's see what you guys come up with. Anybody tell me what the modulus of elasticity is for that section? Somebody tell me. We're looking on page 602 and 603 for a W12 by 50. Anybody find that?
Good on 602.
603 actually, that it starts on 602. You're looking for the modulus in the XX axis.
391.
391, and that would be what unit? Moment of inertia is what?
It would be inches to the fourth.
Correct. Inches to the fourth. I want to look at the units here, so you got to be careful with this, okay? That's the only thing when we do these problems that is really, really important. Okay, so the other thing we need is the length expressed in terms of inches. So we have 20 feet. We're going to convert that to inches. We're going to multiply that by 12, and that's going to give us
240.
240 inches, correct. Okay. So the other thing, and this thing gets you all the time, is the loading rate, W, okay? That W value, this is called your loading rate, is in what unit? It is in what, 3 kips per foot, right? What you want to convert that to is kips per inch. Now, if this was in kips and this was in pounds, we'd have to be careful too, because remember, you want to match typically what's going on with your modulus of elasticity. So the force unit is fine. That'll cancel, but we got to get this in kip per foot. So how do we do that? I'm sorry, kip per foot to kip inch. Kips per inch. How do we do that?
Just multiply it by 12.
Yeah, and you just blew it. All right, watch your units here. Well, there's what, 12 inches per 1 foot, right?
Mm-hmm.
So feet is going to be on top, 12 is going to be on the bottom. You see that? Now, you're not multiplying by 12 in this case, you're dividing, so you have to really be careful with that. That's the natural inclination, is that you would multiply it, and what you would do is blow this by a factor of 12. So now we're in the proper unit. This is kip inches. Okay, does everybody see what I did there?
Yep.
Okay, so look at that table 12. There's 1, 2, 3, 4, 5 different situations there. Which situation do we we've got a what, uniform load, correct, across that beam? So we're looking at the very top equation, right? That says delta, which is your deflection amount, is equal to 5 times W. W is your loading rate, times L to the 4th, divided by 3. Is that 84? That's a constant. So that's also a unitless constant. So that has no units involved. Then E times I, there's your beam stiffness. So essentially we can just plug everything in, but remember we got to make sure that the units are going to work. We just made sure of that. So what we're going to wind up with is when we cancel everything out, this is going to be in inches. So I'm going to go ahead and put this in. This is 5 times W, which is 0.25 kips per inch. And then we have L is 200. Oops. It's 240 to the 4th. So that's going to give me inches to the 4th. And we are going to then have at the bottom 384 times E, which is 29,000 KSI. Okay, so kips per square inch. And then E, which is 391 inches to the 4th. So inches to the 4th, they cancel. You have inches, that's per square inch, and that's inches. So those are going to cancel and leave you with inches, and all of your kips will cancel out. So when we run this number, let's see what we come up with. And it's going to be hopefully not a really, really big number. Let's see what we get. If you do get a really big number, you've probably got a problem. Here's what I got. You guys verify this. I got 0.952 inches. Anybody get that number? I'm taking that times that to the 4th, divided by that times that. And this right here, this term right here is referred to as your beam stiffness. Is everybody getting that number? Anybody?
No, but I think I did something wrong.
Yeah, I mean, it's possible depending on how you key it in. It's real easy, so be really, really careful. But like I said, my calculator doesn't work real nicely, so I don't use brackets. If you're trying to use brackets, just be careful. I don't even have a y to the x key, so I have to do this squared and then square it again to get to the 4th because my calculator doesn't let me do it any other way.
Got it.
Okay, did you get that now?
Yeah.
Okay, so what that's telling us, at midspan, that's the maximum deflection. So it's not even an inch, right? So let's put a little wrinkle in this. All right, if we have this loading scheme right now, okay, and we add another force here, let's just add a force right in the middle. So I'm going to add a force in the middle right here. And that force is going to be coming straight down midspan. It's going to be a 60 kip load. Well, obviously that thing's going to deflect more. But if you look at those diagrams there, you don't have any formula that relates that and that at the same time. But what you can do is calculate this one using this equation. And if you notice right below it on the table, for a concentrated load at mid-span, they have another equation that says your mid-span would be equal to your force times L cubed divided by 48 EI times the beam stiffness. So what we can do is use a process called superposition, which basically allows you to calculate the deflection here. We can call this deflection 1, and we can calculate deflection 2, and your total deflection then becomes the sum of those two guys. So we can see by putting this at mid-span plus having that uniform loading rate, we can see what's going on. So this is really just a plug and chug again. 60 times 240 cubed divided by 48 EI. Let's see what we come up with here. So 240 cubed times 60 divided by 48 divided by 29,000 divided by 391. I came up with a heck of a lot more deflection. I get 1.52 inches of deflection. So by summing these two guys now, you have 0.952 plus 1.52 . That gives us basically 2.47 inches. Okay. So that's beam deflection concepts. And that's actually, if you think about that in 20 feet, think about that. That says that that beam's going to deflect almost 2.5 inches. You're going to feel that, right? I mean, that's a lot. So let's look at that, how that works with an allowable situation. If this beam was a roof member right now that was supporting a plastered ceiling, and it's a dead load plus a live load, let's say, does this meet the allowable? Well, the allowable deflection in that case, if you notice on that chart on table 12.2, if this is a plastered ceiling, let's say it's a floor member, but it's the same. For a floor member, dead load plus live load says that your allowable deflection for this member would be L divided by 240. So L is going to be 240 divided by 240. What's our allowable deflection? 1 inch, right? This exceeds this, so this wouldn't work, would it? Under those conditions, if that's what your building code says. So guys, if this is the case, if this is the allowable for that situation, and this is what we're coming up with, what do we do here to fix this? How can we get that number down and or that number down?
Taking the beam.
Yes. In other words, increase what? The moment of inertia, right?
Mm-hmm.
Yeah, because if you're steel and you're gonna have to use steel, then you know you're not gonna change this number much, okay? But by increasing the depth, I mean, if we're at a 12 by 50, maybe we go up to a 14 or a 16, a W16 by something. That'll increase the cross-sectional area, which will increase the moment of inertia, get these numbers down to acceptable limits, okay? Kind of see how this works?
Yeah.
It's not very hard. It's just the biggest thing when you use those equations is that you make sure that you're utilizing those guys in conjunction with those units. Okay, make sure you watch the units. Okay, before we get done with chapter 12, I want to show you one more thing. Let's go back to appendix in the back of the book. I want you to show you appendix D real quick. Okay, appendix D. If you would step back there for me. In appendix D, what you'll notice, this is for timber design. And why that's important is in some of those designs that you're getting into or that you're looking at in chapter 12, you're using wood or you're using timber. Go to page 644, table D1, and you'll notice it gives you nominal size and then it gives you what's called dressed size. So when you're calculating cross-sectional areas, for instance, let's just clean this page up real quick. If they tell you you have a joist that is a 2 by 12, oops. Let's say you have a wood joist that's a 2 by 12. You don't actually have 2 by 12. If you notice, your dressed lumber size is actually 1.5 by 11.25. So when you do these equations where you're dealing with either moment of inertia or you're dealing with depths, any of that stuff, you're going to have to use these numbers right here to get the right values, because otherwise your cross section is going to be bigger than it should be. Okay, does everybody see what I'm getting at there? The other thing about this chart, which is really cool, if you read over from the dressed size, you will also notice it calculates the area of the section for you. It gives you the section modulus. And remember, the section modulus is I over C. So you don't have to calculate that kind of stuff. And it does give you the moment of inertia. So if you are looking for that 2 by 12, you'll notice that the area of a 2 by 12 is actually 16.88, and the section modulus, which is cool, is equal to 31.64. So you could calculate that. Actually, it gives you the I as well. So all that stuff is coming from that chart for that 2 by 12, the moment of inertia. So if you took 178 and divided it by half of 11.25, you're going to get this 31.64. So this is going to be a real time saver, okay? But that chart applies to timber, and there's going to be, in chapter 12, there's going to be some problems where you do that. So make sure that if they tell you it's a wood 2 by 12 or whatever it is, that you have to get the dressed size. All right, is everybody okay with that? We're going to work a lot more with this on Thursday, so that's kind of leading up into that. Okay, any questions then before we move on?
No.
Okay, all right, so I want you to concentrate on those problems out of chapter 12, okay, which are bending moment, bending stress problems and shear stress problems and deflection problems. There's a few of the deflection problems. I want you to spend the most time on the bending stress and the shear stress, okay? So I'm going to introduce today the concept of combined stress. And we're not going to get too far into this. Like I said, I probably want to stop about 10 o'clock here, so I'm just going to get started so that we can concentrate on the other stuff this week. All right, so let me go ahead and go back to here. I'm going to close this one. Oops. Okay, so we're going to take a look at bending or combined stress. So let me get into my slideshow. Okay, so this one's out there now. This is chapter 13 or a folder. The next folder has been opened up. This is dealing with chapter 13. We're going to spend the rest of the semester with 13, dealing with that. And at this point, by the way, you have everything to do the deck design. So again, that's why I want to concentrate. There's nothing out of chapter 13 that we're going to be dealing with on that deck stuff. So everything is out of chapter 8, 9, 11, I believe. So, okay, so we're going to talk about combined stresses, and this is where we're taking more than one kind of stress and adding them together, essentially. So we're going to be looking at combined axial and bending stresses, because these two things work together. And so if you don't understand that you've got both of those going on at the same time, you're going to have problems. And so again, what's interesting is one will kind of counteract the other too. So you'll have a lessened stress maybe on the top and an increased one at the bottom. So we'll look at that. And if we get time, I might not do any of this, but there's combined stresses due to what's called an eccentric load. So that's a load that's not coming straight down in the middle of your beam or cross section, whatever. It's off to one side. So what that will tend to do is add another bending moment into it. So you may have two moments, one that occurs due to the load itself and another one that occurs to what's called eccentricity. And I'm not going to get into this at all today, but we're ultimately going to talk about combined normal and shear stress along planes, and that'll lead us into this thing called Moore's circle. So the very last thing we're going to be looking at is something called Moore's circle. But I probably will not do anything with that until after Thanksgiving, and that will depend on what goes on also with the college and closures. So we may not even do Moore's circle. So if we don't do anything, if we scuttle that, that'll be the last thing. Okay, so when we talked about the previous chapters, we looked at members being subjected to several different types of stresses or developing several different stresses based on the type of loadings that are occurring. So you can either be subjected to axial, bending, or shear stresses individually. So axial, remember, generates a stress along the cross section. And that means that your area that you're considering is perpendicular to the direction that your force is being applied. With bending stress is subjected or being based on the fact that you have that bending moment going on. And shear stress develops due to forces that are acting parallel to the cross section. So in other words, we have these three things going on, and we looked at them separately as if you're only dealing with axial, bending, or shear. But what we're going to find out is that a lot of times a member is going to be subjected to more than one type of stress at a time. And so from a standpoint of dealing with that, you're going to be looking at combining those things. So because the member actually is experiencing those together, you can't just look at them separately. What you're going to do is combine them and look at the combination. So this is what we call a combined stress. So if you think about this, when a beam is acted upon by a bending moment, it's also being acted upon by shear stresses. Okay, so you got the two things going on, which chapter 12 just considers them separately. Okay, but we're looking at now, okay, well, what happens when we combine them? Because you can actually get greater amounts of stress that are occurring, which again could yield a failure if you're not careful. So tension and compression moments due to your bending will combine with stresses that potentially produce critical combined stress, which means you may have failure. So you have to be able to, as a designer, recognize this and be able to calculate maximum stresses that are caused by that combination or that combined stress. So when we have two or more stresses, it's going to be necessary to break those stresses down into components, and we either look at them acting normal to the plane in question or acting parallel to the plane in question. So if it's acting normal to the plane in question, we call that a normal stress. And That's another term we've been using is axial stresses, okay? So that's just your simply P over A kind of formula when you're dealing with that, okay? So that's what we talked about primarily in chapter 8. Now we also talked about shear stresses, and shear stresses are the stresses that act parallel to the plane, okay? And those are also P over A, but when you're dealing with bending, it becomes a little different, okay? So we'll look at those here in a sec. So when we combine these two things, the stress situation where we're subjecting the beam or the member in with an axial force, then you're going to develop an axial stress, but you're also going to have bending. So these kind of things occur all the time. So one thing that they'll do very often in beams is load them what they call pre-stressed. So what they do when they pre-stress a beam, and a lot of beams are done, especially ones that are manufactured, especially like concrete beams, what they'll do is what they call pre-tension them or whatever. So what they'll do is in the form, they actually put steel cables. They put those cables under tension, and then they pour the concrete around them, let the concrete cure, and then those cables are released, and it pre-stresses that beam into a compressive mode or a tensile mode. That's called a pre-stressed beam. Very commonly used in like highways and those kind of things. Or we can eccentrically load a column, which means that the force is not coming straight down through the column, it's coming off to the side. Or you could have a foundation that's subjected to a lateral load. That means a load that's coming in off the side. And most foundations actually have lateral loads on them. Those are would be like your dirt surrounding your foundation. That's a lateral load. So these things occur all the time. Actual stress that develops in a member is going to be the result of the axial load effect coupled with the bending effect of an applied moment. So that's where we get those two things. So combined stress is produced by that axial stress coupled with the bending, and you calculated it using that concept of superpositioning. So superpositioning is just the principle of being able to calculate one force or one stress one way and another stress another way, and then being able to add them or combine them. So by superpositioning, we're going to calculate the axial effect and the bending effect. And because these guys are collinear along the cross section, we're going to be able to add them. And the one thing about bending stress, it's going to produce both tension and compression. And those can add then directly to the tension and compression of your axial stresses. So the way that the bending occurs, and I think we've looked at that. Let's look at that real quick. Let me draw some pictures here real quick, and then we'll get into an equation or two. So if we're looking, let me clean this up. So if you have a beam, I'm just going to use a very simple beam. So what we're essentially saying is this beam can be subjected to, let's say, a force this way and a force this way. And of course, it's in equilibrium. So if you have a force like this, we'll just call that P. Oops. Call that P for our load. So this would be an axial force right here. So this would develop an axial type of stress. So you would have that axial stress, which is basically a force divided by cross-sectional area. And if you had another load coming down this way on this thing, it's producing a bending moment. So what we were just talking about, due to that moment, at the top, you're going to be in compression. In the bottom, you're going to be in tension. It's going to kind of want to pull apart this way and go this way. So if this is a tension load and this is a tension load, at the bottom, you're getting the tension due to the axial stress plus the tension due to the bending. But in the top fiber, what you're going to see is that you're going to have tension going on due to the axial load or the axial stress, but the compression is going to be kind of the opposite. So what we'll notice is the stress here and the stress here are not going to be the same. And that's the concept of that combined stress that we'll look at. Okay, so axial bending. Now let's go back to the diagrams. So by calculating the effect of the bend of the beam or whatever member you're looking at due to these collinear forces, you can use that superposition and calculate your axial stress and add to that your bending stress. Okay, and again, that bending stress is going to be both in tension and compression, whereas the axial is either going to be strictly tension or strictly compression. Okay, so this kind of shows you that concept. If you recognize that this is showing you kind of a member, this is what the stress is doing in axial. So this is indicating maybe that member's in tension. And due to bending, we have compression going on at the top. We have bending going on at the bottom. By using this superpositioning concept, you're just adding these vectors together. And notice that vector going this way, consider it a positive. This vector going that way, consider it negative. When you add them together, you get a lot less going this way. But when we go down here, this thing is going all the way out more. So this would be our combined stress. And if you notice up here, our combined stress is less at the top of the beam, more at the bottom. Now, you can also have a point, because this is showing you have all positive stress. So you might be, this is saying I'm maybe in tension here and more tension here. But you can actually have this thing kind of look like this. So you can have some in compression and some in tension. So I'll go through an example with you, show you kind of how this works. Okay. So this is the real concept of what we call superpositioning. Calculating an axial stress, calculating that bending stress, combining those guys in such a way that you can then determine your combined stress. But this stuff actually isn't that hard. So here's the equation that we're using, and these should be familiar to you. Combined stress is just combining the axial stress and the bending stress, and the formula is very simply written like this. Your combined stress is equal to your axial stress, which is simply force divided by cross-sectional area. So that's your applied force divided by cross-sectional area, plus the bending stress that develops, which is our equation, MC over I. And the difference here is this is the cross-sectional area that's resisting the axial force. And here we have to calculate the moment if the moment is not already given. So there's going to be different things that you're going to have to look at when you get into this. Okay. And the other thing that we have to look at is that some things we have to consider, okay, with regard to combined stresses. So your bending stress, remember, is going to produce a tensile stress and a compressive stress. So that should say tensile stress and compressive stresses. And they are going to vary from 0 at the neutral axis to a maximum at the outside edge. So if I go back to that diagram here, what this is saying is you're going to have tensile stresses that develop here, compression. It depends on which way your bending moment's going. If my bending moment's coming this way, it's compression at top, tension at the bottom. But at some point, there's typically that 0, which is almost, for a rectangular cross-section, going to be through the neutral axis. Okay, so that's what that was talking about. And it's usually a maximum at the outside edge. So you definitely, as a designer, are looking at maximum conditions, but they also talk about minimum. So in a combined stress, your minimum occurs at the opposite side where the maximum occurs. So it doesn't necessarily mean it's a smaller value, it just means it's opposite. Secondly, the other thing is that the axial stress is going to be added and similarly. So in other words, compression will add to compression or tension will add to tension. But if they're dissimilar, then they subtract. So you add tensile stresses to tensile stresses or compression stresses to compression stresses, but you subtract tension from compression or compression from tension. Excuse me. And the way we handle that is we just assign it a sign value. I'll show you that here in a minute. So here's 5 steps that we can go through when we do these problems. It's very simple to do. So first of all, you identify the axial force and state whether it's compression or tension. Okay, and that's obvious from the way the picture is diagrammed. So if you have a tension force, normally we assign it a positive value. If it's compression, it's negative. So again, this is arbitrary as long as you're consistent, but we would typically use compression is negative, tension is positive. Identify the resisting area, that's the cross-sectional area, and that's going to be used with the P over A. Then you identify the bending moment, and you have to also know the axis about which it's bending. And by doing that, then you have to look at, okay, is it creating compression on the top or tension on the top? So you have to do that. And then again, we want to assign sign values that are going to be commensurate with this. So if you're saying tension is positive here, then tension for your bending will also be positive and compression will be negative, okay? Once you do that, you identify your C value. For symmetric sections, C, remember, is going to be just half the depth. And it's always measured perpendicular from the axis of bending, which is essentially our neutral axis, to the outside edge. You need to determine your moment of inertia, which is relative to your bending moment. Again, that's pretty simple. For certain types of shapes, you can look that up in tables. And then you place these guys into your stress equation. And I'm going to show you an easier way to do that is just step through a very simple chart that we can set up. And then we can also determine where max and mins occur. And I'll show you how we can determine where zero occurs. So I'm going to run through an example problem with you. This stuff isn't really actually, it may seem like it's a big deal, but it's actually very simple to do. One of the actually easier things I think you'll see. So I'm going to look at a problem with you. We're going to go through problem out of the book. I'm going to do problem 13.1 just to show you how to do this. And that might be all we're going to do today. So let me go back over to my little whiteboard here. And let me draw this up. So we have a beam that's simply supported. So we have a beam that's simply supported here. I think I'm going to move this over here out of the way.
Which problem was that in the book?
It is the example problem 13.1.
Okay.
So I'm just going to go through it to show you where all that came from. It's pretty straightforward. Okay. So they give us the cross section. Let me draw the cross section over here. Shows you that cross section is 16 by 1 or 12, or sorry, 10. Jeez. Okay. And we have a beam. Let me do this a little bit better. We have a beam that's simply supported. And it also has a very simple load right in the middle. So mid-span, we got a load. We also have a load here, or a reaction here, and a reaction here. Okay, so what is the load? The load is 10,000 pounds. Okay. They also have a load on this thing axially running this way and one running this way, which happens to be the same because we're in equilibrium. And what's important to note here is that load is coming through right in the middle. So in other words, right in the middle, that's the neutral axis. So it's coming through the neutral axis. When you start to talk about that concept of eccentricity, if this guy is above the neutral axis or below the neutral axis, it's going to create a bending moment on that in another direction. So we'll handle that. We'll handle that next week probably. Okay. All right, so the first thing we need to do is I'm going to go ahead and solve the reactions on this. Does anybody know what the reactions would be on this just by inspection? If this is reaction A and that's reaction B, these guys just cancel out, right? So sum of forces in X equals 0, correct? What about sum of forces in Y? What's happening here? This is 5 feet, and that's 5 feet. What's happening there? This is symmetrically loaded, right? They're right in the center. So if that's right in the center, how much is each one of these reactions carrying?
5,000.
Yes, just half, right?
Yep.
Now you can go through the math and do that. You can do a moment equation and all of that, but we're just going to do that by inspection. Now you're not going to be able to always do that, okay? So just keep that in mind. So we need to get a bending moment out of this to be able to solve the bending piece of the equation, okay? So we have to do, in order to do that, we have to do a shear moment diagram. So I'm going to drop a critical line here and a critical line here. Where's another critical line? Develops what? Right on that load, right? Correct? And I'm going to have my shear right there. And I'm going to have my moment here. So this is where that shear moment stuff starts to come into play, okay? So we start out, if we have a reaction here, we have shear coming up, and it's going to hit it at 5,000 pounds of shear. What happens as we step across this beam? Is it increasing, is it decreasing, or is it staying the same?
Constant, staying the same.
It's a constant, right? So this is a constant, stays at 5,000, then it hits the 10,000. 10,000 negative plus the 5,000 gives us a negative 5,000, right? And then it steps across and it does what? Stays constant, right?
Yep.
And then it comes back and we're good. Okay, so we know that our reactions agreed because we indicated 5,000. We started out with shear, stayed constant, hit 10,000, went to negative, and that added together gives me that. So I have generated two areas here, area 1, area 2. So there now is a moment. Moment we know is starts at 0, and then it'll be based on area 1. So area 1 is going to be what, 5,000 times 5 gives us 25,000 pound feet. So that's going to go like this. That's going to be a linear relationship. It's going to do that. And that's going to be 25,000, and that is pound feet. Sorry for my units. Okay, and then this is going to be a negative 5,000 times 5. When I add those two together, that's going to bring me back to 0. Okay. So I now know that my maximum applied moment is 25,000 foot-pounds or pound-feet. Okay, is everybody okay with that? We good? Any questions on that?
No.
Okay, that was chapter 11 stuff, right?
Yeah.
All right, so now then we have the equation that says combined is going to be axial stress plus your bending stress. Okay, so I'm going to handle it in 2 steps. And one thing I'm going to do here is we're going to say that tension, we're going to define tension stress as positive, and we're going to define compression, a compressive stress, as a negative value. Okay, now that's arbitrary. I can do that any way I want, okay? So I'm going to look at this component first, and that is based strictly on this guy right here and the cross-sectional area. So remember this is axial, so the cross-sectional area is running this way, so that's what this section is here for. So for the axial force, the P over A, it's developing a stress of what? Force is 50,000 divided by 10 inches times 16 inches. Let's see what we come up with there. I get 312.5. You guys getting that? PSI. Does that make sense?
Yep, that's what I got.
Okay, so now let's think about that, because we know that we usually indicate this as that stress is the same thing for this whole cross section here. We're saying that stress is 312, even though it's being pushed or pulled right there. We're saying no matter where we measure that, it's that same number. That's not totally true, but that's the average, okay? And since this is pulling, we're going to call this a tensile stress. So we're going to call that a plus. Does everybody follow me on that?
Yeah.
Okay, so now, if we look at this moment that's being induced on this beam right here, it's pushing like that, so it's putting me in compression at the top and tension on the bottom. Does everybody agree with that?
Mm-hmm.
Okay, so we're going to calculate MC over I now. So we need, M we know is 25,000, right? What is C? C is the distance from the neutral axis up to the outside edge fiber, right? From the neutral axis, which would be 8 inches up, 8 inches down, out. So C is going to be 8 inches, correct? Is that right?
Where are you getting that 8 from again?
If we look over here, you see my cross section here? There's my neutral axis.
All right.
Since that's a real rectangular shape, it's going to half the distance, correct?
Yep.
And C is always the distance from the neutral axis out to where you're considering, but since we're looking at a maximum condition, what we're looking at is the tension or compression out there, okay?
Yep.
So the other thing we need is I, and I is defined as what? 1/12 the base, which is 10, times the height cubed. So this will give me the bending stress at that point, okay? So let's see what we come up with. Be careful when you do the math here. I already blew it. We'll see what we come up with. Oh, geez. Anybody get a number? I had to do it about 3 times before I got one. I made a mistake already. Anybody see my mistake?
Nope.
All right. Yeah, I just did this, and this is a good mistake. What are the units here? This is what? Pound feet, right?
Mm-hmm.
This is inches. This is inches to the 4th. And this is in pound feet, right?
Oh, so you need to convert it to.
We need to convert it, don't we? Yeah, that was a good mistake. So this actually, I have to multiply this by 12 up here too. Okay. Multiply that by 12 gives that. All right. So if you, whatever number you came up with, if you multiply it by 12, will be good. Well, that's a good mistake. So I came up with, it's good to show you that if you're not careful, it's really easy to make a mistake on this stuff. I came up with 703.13. And this is going to be also PSI. See, I would not have been in PSI. I would have been in some funky unit, which would have been incorrect. Okay. Try that now and see what you guys come up with. If you don't like calculating I this way, you could calculate it before you plug it in also. But just remember, this is inches to the 4th. C was in inches. This also has to be in pound inches. Okay, so units, big thing here, okay? Anybody getting the 703 number?
Now I'm trying to plug it into my phone because my brother still has my other calculator, so it's taking a while.
Yeah, it took me a couple of times too, Jacob. So got to
That's what
watch.
I
Sometimes,
got.
like I said, it might be easier to calculate I first. Does somebody else have a question, Max, or
No, I just said that's what I got.
you agree with that? Okay.
Yeah.
All right. That should be correct now. So I made a mistake there, which would have been really detrimental. Okay. So you guys need to watch that too. It's real easy to do. Now, if we agree that this is the number we're coming up with, and this is what we should have, then we got to look at this. It's telling me at the top of this beam, that's compression. So that would be a negative, but at the bottom, it's tension. So this guy has both a positive and a negative value to him. Okay. Both positive and negative. So how do we handle this now? So we generate a little chart here. So we're going to say at the top, we got one thing going on, and at the bottom, we got another thing going on. So for our axial stress or our normal stress, at the top, it's going to be plus 312.5 psi. And at the bottom, it's also 312 psi because that's the same value whether you're top or bottom, because it's a tension force, so it's a tension stress. Okay. If we look at the bending stress, we just said that at the top, we know it's 703.13, but we know it's compression, so we're going to call that negative. And at the bottom, what we have is tension, so it's going to be plus. So our combined stress is just adding those guys together algebraically. So what we have is 312.5 minus 703.13. So I get a negative 390.6 doesn't mean you have negative stress. It just means you have compressive stress. That's all. And at the bottom, we have a positive, and this would also be PSI. So the maximum point of stress is at the bottom, but it happens also be a tensile stress. Everybody see how we did that? You guys getting those numbers? So these are the numbers we're after right here. That one and that one. So everybody seeing that? Anybody get this, Max? Irvin?
Yeah.
Yeah, I got it.
Okay. You guys understand what we did there? Calculate the normal stress, then the bending stress, but we had to apply
Oh,
these.
never mind. I see.
Okay. We had to apply those signs based on what we're looking at the condition. Does everybody understand that? So if this force had been going compressively, this would have changed to a negative by virtue of the fact we're saying compression is negative, tension is positive. Okay? Does that make sense now?
Yeah.
Okay, so one of the things I will show you can also do with this is you can plot what's going on here. Let me do this real quick. I'm going to get rid of all this junk here. We're going to do a real quick little plot just to show you now that we got these numbers, how we can do this. Okay, so you can generate a graph that's showing you what's going on through that cross section. So let me draw a diagram here. So if this distance represents the distance from that edge to that edge, okay? That's the 16 inches. And this is the vector in compression. And this is the vector in tension. Okay. So this number up here represents negative 390. This one represents positive 1015. So what we have is something going through it like that. So what you got going on here is this is the total amount of compression. This is the total amount of tension. So we have 15.6 and negative 390.6. So what you got is all these little vectors. They're approaching, as you go down this way, it goes to 0 at some point. So at that point right there, you've got 0 compression, 0 tension, but that's not at the neutral axis. Okay, so if you wanted to know where this location occurs, where is the point of 0 stress, you can solve this little proportion. If you look at this similar triangle here, this distance here is 16, and this edge here would be that plus that. So I'm going to write a proportion that's going to say 16 is to the sum of those two. And I'm not summing them algebraically. I'm looking at the absolute value. So I'm going to take 1015.6 plus 390.6. So in other words, I'm looking at that triangle that looks like that. This total face here is just that plus that over 16. And if I call that guy, we call this guy X here, that's going to be equal to X. In this X is going to be equal to that distance there, which is 1015.6. So we can solve for X. And we get 11, basically 11.56 inches. So that's saying the point of zero compression, zero tension stress is 11.6 inches above the beam bottom or the difference down. Okay, so you'll see that very often done, and you can determine that based on that. So this little chart kind of does all of your work once you get all your numbers, but notice this is a pretty good step process. You had to calculate your axial stress, you had to go through a shear moment diagram to get your maximum bending, then you calculate your bending stresses, and then you have to assign those values to get those, okay? We're going to be working through these problems, but I'll tell you what, this actually isn't that tough to do, okay? So anybody have any questions? This is probably a really good spot to stop. And I'll pick up with eccentric loads next week. And if we have time, we're going to go into Morse circle, okay? But probably not. All right, we all good for now?
Yeah.
So what I want to do then, I want to concentrate on chapter 12 problems on Thursday, okay? And we'll work all of them that you want to. There's quite a few in there, so I would say spend some time doing that. And they're mostly bending problems, bending stresses and shear stresses, and then there's a couple of deflection problems to do that I've assigned. And then if we have time, we'll start into some of these on chapter 13. So you can do some of those initial problems on chapter 13, but don't do anything that's an eccentric loading, okay? Just do the simple ones. And then we'll pick up with eccentric loadings. We'll see how we do, okay? So the other thing, I have the test back. I want to go over the test the first thing, and we'll do that first. We'll take a look at these problems, and also make sure you bring your deck project stuff with you so that we can take a look at that. Okay? Any questions then? Go ahead.
So I just want to make sure. So then it is being pushed back then, the due date?
Yeah, definitely, because we're just not ready for it. Yeah. Would I have it for this week?
Yeah.
Yeah. Don't worry about, well, when I say don't worry about it, I want you to do something. I'm not sure what people have done. So bring in anything, because we've got to look at, there's 4 sections that we need to look at. Okay. You got to do your tributary area. You got to do your reactions. You've got to do your shear, which we probably haven't done. And then you got to do shear moment diagrams. Okay. So you could actually do your shear moment diagrams without doing the shear bolt issue. So just bring in what you got, and I'm going to run through it start to finish. Okay. But yes, we're definitely pushing it back. So it'll probably occur that week after Thanksgiving, and hopefully we'll still be able to meet, but if not, then you'll have to submit it to me, okay?
Yeah.
So are we not doing anything the week of Thanksgiving, or are we still meeting that Tuesday, or what?
We'll probably meet that Tuesday, but I'll probably just go over, well, I'll probably go over eccentric loads with you is what I'll do, okay?
Okay.
And then clean up
Thursday?
anything. Yeah, and then Thursday we don't meet, obviously, so there won't be anything going on Thursday.
Okay.
Okay?
Yep.
All right. So I'll go ahead and I'm going to stop the recording, and we'll get this guy, I'll get this formatted. You can go back and look at that. There are the 2, I did add stuff to the chapter 12 stuff that has the deflection stuff in it. You didn't have that before.